Now let's take a look at this next equation. It is that of a square root graph. Notice the smallest number that can be substituted in is -1, because we know from the domain that x plus 1 must be greater than or equal to 0, and therefore x must be greater than or equal to -1. And when you substitute -1 in, you get 0 as an output. So -1 comma 0 is on the graph, and it turns out that 0, 1 is, and that 3, 2 is on the graph, and so we have this half parabola graph for f of x. And that will need to be one of the graphs you have memorized when you move on to college algebra. Not now, quite yet. Now, let's go through and switch the x and y. Instead of y equals the square root of x plus 1, I'm going to change this now to x equals the square root of y plus 1. And then I need to isolate the y, which means squaring both sides. I get x squared equals y plus 1. And then isolating the y, subtracting 1 on each side, we have x squared minus 1 on the left. Now you notice that to be the graph of a parabola. And if I graph that, it starts here at a vertex 1 unit below the origin, and we end up getting this curve. Now you can tell very quickly that these are not reflections across that diagonal line, because there really shouldn't be two halves to this parabola. We only want that right side, and we really don't want this left side. And so in order to find the inverse, which is going to look like this right here, f inverse of x, we actually have to restrict the equation. And so what we say for this problem is f inverse of x is equal to x squared minus 1, comma, where x is greater than or equal to -1. It tells us we're only looking at the right-hand side of this graph. Now, to prove that two functions are inverses of each other, basically you need to compose f with inverse and f inverse with f and show us both times that we get x coming out. So in this problem we're given f of x and g of x, and let's take a look first at f composite g of x. This is where the g of x gets substituted into the f of x. Now f of x says find the cube root of input plus 5. Now g of x, which we're substituting in, is x cubed minus 5. And you can see that 5 and -5 are going to cancel each other out, and we're going to have the cube root of x cubed, which is then equal to x. So far we've got half of our proof done. Now what we need to do is we need to look at g composed with f of x, where f gets substituted into g. And now g says input cubed minus 5, where the input function f is the cube root of x plus 5. So the cubing undoes the cube root, and what we get is x plus 5 then minus 5, which you know is x. And since we can compose in both directions and get x, we have proven that f and g are indeed inverses of each other. Now let's look at a couple functions that are a little bit different. This first one is different because we have 5 points representing the first function instead of an equation. Now let's take a look at what we're being asked to find. The first thing is g inverse of 5. In other words, go backwards, start with the 5 output and find the input that it comes from, which is going to be 1 as I've illustrated up above. H inverse of x, that's what we've been doing all along. Take the y equals 2x plus 3, switch the x and y to make it x is equal to 2y plus 3, and then solve for this new y. Subtract 3 on each side to get x minus 3 is equal to 2y, and then divide each side by 2. And that will give us y, or h inverse of x, is equal to x minus 3 all over 2. Now this next problem is actually just kind of a trick here. You're supposed to know that inverses undo each other, and so when you stick -4 in as an output, you're supposed to have -4. No math to do, just an understanding of the concept. Now let's look at this next set of problems. They're telling us to find g composite f of x. So f of x gets substituted into g of x. G of x is the absolute value of our input plus 2. And the input is the square root of negative x minus 2. And so that basically becomes our answer for the composite function. Now, it wants us to find the domain of this, and really there's no restriction with absolute values or this plus 2, but what's underneath this radical here, this negative x minus 2, must be greater than or equal to 0. So let's solve this. Let's add 2 to each side and have negative x is greater than or equal to 2, and divide by negative 1, being careful to change the direction of the inequality, and so we'll have x is less than or equal to negative 2, and the domain of this composite function will be from negative infinity on up to negative 2, which we include.